morning, everybody. So in this talk, I'm gonna speak about the context of near memory and transprecision accelerators. So two different domains, accelerators that combine near memory, we put them near to the memory, and also we combine techniques about transprecision. So we are using CAPI and OpenCAPI and Snap framework for that. So I'm gonna start with a little bit of the baseline and a little bit of the performance when it comes to just a system, let's say, very simple case, CPU memory. And the roof line is really a nice, let's say, idea to depict what are the true roofs of a system, like the CPU computation roof and the CPU memory bandwidth roof. Okay, so when we have an application, it can be either memory bound or compute bound, depending on the arithmetic intensity. So arithmetic intensity is how many operations a specific application has in the context of how many bytes does it have to transfer from the main memory. Okay, so we do know that the optimal point is always on this side, on a system, right? Because on this side, we do know that we do not underutilize either the bandwidth or the CPU capabilities. So when it comes to the future chips, to the future CPUs, what do we expect? And really, we don't expect that future CPUs will gonna go all over the line, let's say, on this roof line model. Because we do know that the future is not thousands of cores, right? This comes from the dark silicon perspective, the end of Moore's law, end of Tennant scaling. We do know that we're not able to pack more cores on that side. So we don't expect really high gain over here, right? So this is what chip makers are most worried about because of the power density. So if specialization is the future for the hardware accelerators, how do we do it? And we do know that, of course, going from CPUs, if we can trade off the flexibility on the software side and on the system side, and going to the, let's say, to more specialized hardware, we do know that we can gain efficiency, both performance efficiency and energy efficiency. So if we take a simple case, so it's a very nice study that is summarizing one of the emerging areas like Bitcoin. And you can see here from CPU to GPU, FPGA, and async that we can have order of magnitudes of throughput per area and energy efficiency, right? So we do know that this works well. But how can we really say that we can leave the programmability outside of the loop if we go all the way down? So it makes sense that we couple accelerators to our systems and we give these accelerators the capability to increase our roof line, our CPU roof line, and our bandwidth roof line. But of course, we have several questions on here. What we do with coherency, latency, throughput, DMA scheduling, programmability. And this is why CAPI and OpenCAPI technology really give an answer to all of these questions, because it can really connect our accelerator's memory with our system memory. Our accelerator can have an access directly to the main memory like CPU, and of course, we can get the advantage of these new roof lines on our system design. Okay, so we propose here to use near memory accelerators, and specifically, we propose to design accelerators that when it comes to the internal memory, we don't rely on caches, but we do rely on scratch pads, okay, that we can specifically design in a way to avoid all these misses on when it comes to accessing the memory over here. So I'm going to show some examples how we do specifically that. And what does it mean to use near memory accelerators for the roof line? The notion here is that we can, either if we have an application that is memory bound or compute bound, we can, of course, have an advantage on the vertical space of the roof line, right? We can quickly jump on the roof line. And the other let's say, area that I'm going to discuss about is the transprecision computing. So transprecision computing is another form of approximate computing, with the difference that we have the option to change the precision during the computational progress, either statically with the predefined metrics or at runtime with some metrics that we collect from the runtime system. Okay, so the direct advantage of the transprecision is that we can shift on the right side on the roof line because we have to do the same operations by fetching less data from the memory. This is the case of the POSIT that we've seen before. Using POSITs, you can go and fetch less data from the memory. And the indirect advantage is that typically accelerators are coming with better performance when it comes to lower precision, right? Because we have GPUs with float 32, but when it comes to float 16, they can deliver as double the performance. So this is the indirect gain when we do. So we're proposing to combine these two techniques, near memory computing with transprecision computing. Okay? So let's see some ideas in practice. I'm gonna speak about the HPC domain. We have some stencil accelerators here and also some ML workloads. I'm start with the baseline system that we have here is a Power 9 Witherspoon machine with two options for accelerators cards that both of them can support in a different way near memory computing and transprecision computing, right? We have GPUs V100 and FPGAs, 89 V3. And let's start with the first example about the HPC. So we do know that stencils are used like at around 30% of the total HPC applications, from fluid dynamics, image processing, weather modeling. Here, the example that I'm referring to is about weather modeling. And we do know, okay, this is just a little bit of introduction of how these stencils are working. We do know that here is a 7-point stencil, and we do know that the patterns are not really very friendly in terms of cache accesses, right? We do know that we have to read these points and to write in one single point of the memory. So we do know that we expect some kind of misses when the order is getting higher. So here it's just a small 7-point stencil. Of course, we have in true weather modeling, we have more complex stencils like than the previous one. We have kind of several stages of stencils by the stencil in the 3D space. And then the memory accesses are really more complex. So here is a roof line of our system that is showing the CPU performance with the DRAM bandwidth, the cache bandwidth. This is a logarithmic scale. And here you can see what we can get if we optimize our horizontal diffusion, the kernel that I've referred to previously, on this system. This is the baseline performance for one thread and for 64 threads. So it's about one socket, okay? Here is the arithmetic intensity of our application of 8 horizontal diffusion. You can see that it is relatively low, so it's a memory-bound application. We've created a design using CAPI and CAPI Snap in order to create accelerators for this horizontal diffusion on this side. So we have the runtime system, the host, the FPGA, and we've used a specific accelerator. But when it comes to create more accelerators, to scale the accelerators, then we've realized that there is a bottleneck over here because of the memory. Having just a small block RAM that can feed your accelerator is not enough. Because as we've seen previously, we have different access patterns. So what we've proposed here in this work was to partition these memories in a way so we can control the partitioning with Vivado HLS very easily. And then we've partitioned the memories in a way to increase the memory bandwidth between the on-chip memory and these accelerators. And for this work, you can either use block RAMs or ultra RAMs, which offer higher density on the Xilinx FPGA devices. So what we're doing is that we're taking the Cosmo model, which is a typical model for weather modeling. We decompose this model to specific subdomains, and then, we go all the way from the cache lines to the registers. We unpack the data to the FPGA, and then we copy the data to the on-chip DRAM of the FPGA. Then we do a kind of a partitioning, a slicing, and then we map all this data either to block RAMs or URAMs. This process here is the trick to increase the bandwidth for the accelerators, to partitioning the memories on the chip. So this work we presented in FPL this year, and actually we did a kind of exploration of what is the best format to work on, right? So here we've experimented with fixed point arithmetic, floating point arithmetic, and POSITs. And here you can see that depending on the accuracy that you want for your device, like 100% accuracy, you can, here is the total number of bits in the vertical space. So you can see that instead of 32, you can use, let's say, 20 for this particular example to maintain 100% of accuracy. And this one is changing depending on the data type that we're using. As I said, we've experimented with float X, which is a library that gives you the ability to really choose any kind of bits for the mantissa and the exponent, and also posits. So here are the results. The outcome of this study is that we can reduce more than 50% of the total bits, depending on the accuracy that you want to keep. So the accuracy has a different meaning for every application. Keeping 90% or 99.9 has a different meaning at the end of the day for each application. So it's about every time do simulations and verify that I'm nice with 90% of accuracy. So we did the simulations, and then we've used the previous design to go to implement it, and this is the results that we get. So here is for the block RAM, and here is from the ultra RAM. We've used 3 different windows, 8 by 8 by 8, 16, and 32. And of course, you can see that 16 or 32, we couldn't use it for all the accelerators. Here is the scaling 1, 2, 4, 8 accelerators. Of course, at some point, we saturate the number of block RAMs or URAMs, so we couldn't implement it. But here you can see the gains, 2.5 with the best with block RAM, and 3.3 the best with ultra RAM. And then is the total aggregated results for this example. So it's a little bit of complex here, but you can see the CPU roof line. Here is the FPGA roof line, and you can see that these are the 3 different applications: 7-point stencil, 25-point, and horizontal diffusion, different arithmetic intensity for all of them. And you can see here the baseline, the optimized solution with the rectangles, and all the solutions that are FPGA with CAPI snap are shifting because of the lower precision and the context of the near memory accelerator towards upper performance and a little bit to the right because we increase the arithmetic intensity. Okay? So this is one example, and let's jump to another example, which is based on the machine learning domain. So previously to the demo that we've seen before, okay, I don't have a demo here, just I have an output of the demo. So we said, can we really build a demo with ML and using our machines, CAPI, CAPI Snap, and FPGAs, and all these accelerators that Power 9 can deliver? Okay, so we said, let's say that we have a laptop, we take a camera input from the laptop, and over the Ethernet, we send frames to our server, and then we process during our throughout our accelerators. Here is a YOLO V3, being an example, and then we get the result with some optimization that probably we need to do because of the classification inaccuracy. But okay, so we've been able to do that, but the problem is that this, if we think about the economics of the cloud, right, it makes sense that if you have such a demo and you have such a system on the cloud, it makes sense that you can access it through, let's say, cloud-native applications, like, let's say, some kind of multi-tenant. A lot of users can access the same system. So we said, okay, let's scale this demo to 10x or 20x. So have 10 laptops or 20 laptops or smart devices that sending this request to the server. What is happening? And this is what happened. Okay, this is what happened. I'm going to refer to this later. So it's again the roof line with all of our accelerators, GPU with a magenta, CPU with the red line, and FPGA with the blue one. Of course, in that case, in the case of dense matrix multiplier, which is what YOLO V3 has, FPGA cannot deliver the same performance with GPU. We do know that GPUs are better in dense matrix multiplier, right? But here I have also another really important metric, which is the power. And we have 300 watts for the GPU, so you can see that we have multiple, let's say, roof lines, depending on which precision you are using. If you are using double point on single point precision. And you can see very easily that we've used in the previous demo 10 containers or 20 containers on this particular example. You can see that the performance can drop by 50x Of course, this is expected, right? Because we request on the same GPU, so this is an example just for the GPU, to do the processing. And we see this performance that drops. So if the performance, the idea here was what? We have a system with some accelerators, GPUs and FPGAs. If the performance is about to drop so much that is falling within the performance envelope of our FPGAs, which operate on a one time of order less power, let's say, output, like 25 watts instead of 300 watts, why don't we just use the FPGA for this particular scope? So this is what we did, and this is what OpenCAPI technology is offering, right? Because we have our Power 9 system, V100, 9v3, explicit with their memory, and here is what OpenCAPI and CAPI technology is giving us, the ability for all of these accelerators to have a common view of the same memory. And we've built it on this environment, so we've created a plugin of the Docker that allows you to use the same gem, let's say, matrix multiplier workloads, dense matrix multiplier workloads, without know if this workload will be spawned either to the GPU or to the FPGA. So this is happening transparently from the user space, okay? And we've leveraged it on a cloud application, a cloud environment like Docker. And okay, this is a lot of about the technicals, but the idea here, I'm not gonna spend a long time, but the idea is that you have your host environment running Dockerized applications, then you have your GPU, your FPGA, and over here, we instantiate a specific module that can really operate in that way, okay? So it's a little bit complex, but I don't think that I have the time to elaborate more, but I will be happy to, let's say, later comment on that side. So with red color is the components that we needed to add to CAPI Snap to allow this to happen. And this is a little bit on the results that we've gained so far. So we've tested 3 applications from the ML, deep speech, language modeling, and YOLO v3. And we've used transprecision techniques in order to not just using floating point, but using other data types. Of course, this always depends on the application. If the application allows you to use less precision, right? So for the deep speech here, you can see on the CPU, using floating point 30 is the only way. With the GPU, you could split between CPU and GPU, okay? The portion of how much of this can happen on half precision or full precision depends on the application. So you can see that this percentage is changing for all these applications. But the really interesting thing is that in YOLO v3, you can really play a lot with more aggressive optimization because you have an impact on the accuracy, right? So you tune your application, and when you fail, let's say on the accuracy, on the top accuracy, like 92, 1.2 for the top 100, you can say that, okay, I cannot use 5 bits for that. I have to use 6 bits for that, for this dense. I'm only speaking now about dense matrix multipliers. We haven't mapped the complete neural network on the device, right? Just only dense matrix multipliers. And here are the aggregated results. I have more, let's say, detailed results of each one of the applications, but this is what we've achieved so far by combining this idea for 10 containers on the cloud. We've been able to increase both the performance by 59.3 in terms of tera operations per second, and also increase the energy efficiency of this design. So, concluding this talk and looking on the path forwards, we've talked about near memory and transprecision accelerators and how can we combine this together. And we do believe that this is a sustainable form of specialization for systems today, using a technology today, not a future technology, but something that we can really grab and use it. And we've talked about 2 domains, HPC domain with stencils, ML domain with dense matrix multipliers, and the advantages for each one of these applications. We do believe that the path forward is agile hardware and productive ways from algorithm to HDL. And of course, OpenCAPI and Snap are paving the way towards that direction. Okay, so We do know that Moore's law is over. In an optimistic way, the hard work now begins, and it will be fun to be part of it, all of us. And I would like to acknowledge both the OpenPOWER consortium that is delivering these systems today, which is, as we're going to discuss later, is really a huge stack. It's not just the hardware, it's the software, the middleware, open ecosystem with cloud-enabled software. It's the complete stack, right? And also the project that I'm involved as regards to from my institution, IBM Zurich Labs, which is the OPERCOM, is an H2020 project that is actually developing all these techniques of tuning the precision, okay? And a lot of libraries have been used in the previous examples from this particular project. So at that time, I would like to thank you for your attention, and yes, I think that